Yeah, ladies and gentlemen, welcome. I was a bit confused because my colleague told me we are not here, and we're not on the list there, so I have no idea. But I think you are here, I'm here, so at least this point is not that difficult. Welcome to another session of biomedical microsystems. And this is today about all the wireless stuff, and it's mainly about inductive coupling. And this could be boring for some of you, for other of you it might be completely new, so this is again one of those things where I have to find the correct intersection of knowledge, which I try to my best. I think even though if you might have had it in your former life in whatever fundamentals of electrical engineering, could be good to revive and reanimate that knowledge when it comes to medical devices. So, what I like to share with you is the physical background, that we get an idea what is the physics behind energy transmission and energy supply and data transmission, what are concepts for electronic circuits, and how should we decode data. And this is something that is not focused on implants or telemetry as such. There's always, if you start with something, that discussion if everybody should reinvent the wheel or not. You might have heard that now in autonomous cars and autonomous driving, that there are certain consortia who reinvent the wheel with different concepts. That's the same with electronic cars. There are gazillions of different batteries, there are different concepts of control, and it will take 10, 20, 30 years, my estimation, I'm a bit afraid of that, until things converge again. That was the same with computer mouse cables. They all had different connectors in the very beginning before certain companies decided to share common connectors. I mean, it took, 30 years now to minimize the number of mobile phone charging connectors or something like that. We still have now 2 worldwide, at least, if we throw away all the old ones. And that is the same with data transmission protocols. It might happen that everybody reinvents the wheel again because of the other thing costs something, or I have something that doesn't fit, and then the portability is less good. But this is then the last step for today. So if we talk about wireless, it's mandatory for implants, I would say, since none of us really prefers to have pieces sticking through the skin. There are still some experimental devices where there are connectors through the skin. We know that from the Utah array, that stuff to record signals from the brain, which are presented here. We all know that from dental implants. If you get dental implants, there's a screw into your bone, and the crown is on top of that, and that penetrates the skin in the mouth. That seems to work if you take care of certain hygiene and brush your teeth and flush your mouth, then it seems to work. And there's another device, a bone-anchored hearing device, where the sound is transmitted via vibrations, and some of them are anchored with a fixation aid that is placed in the bone and sticks through the skin. So there are possibilities. There are 2-3 companies who have prostheses who are fixed in sockets that consist of a metal rod that sticks through the skin and is fixed with inside the bone. If you have very high amputations, for example, and your skin is prone to some pressure source, then this option could work out. But all in all, if you not know how people behave, it's better to put everything under the skin. And therefore we have violence transmission. Or to increase mobility, if you would record an ECG, for example, as we had over the last weeks, some examples. If you record an ECG, it could be nice not to carry all the cables and the controller on your belt around, but to have it somehow wirelessly, that you can place your controller wherever you like to, in whatever pocket, and have the rest as a self-adhesive foil on your chest, for example. So there are many good reasons to do so. Depending what you like to do, we have a relatively high data rate. And this is something that is of importance. If you have a low data rate and it's just about the status of your battery, I could shout towards the implant, "Hey, implant, what's your battery status?" And if the implant murmurs something that I don't understand, I could ask twice or 3 times. It would not matter that much. And asking, resending data would mean within a second I get everything. If we have, let's say, brain-computer interface as the most sophisticated one, or even a cochlear implant, and you want to listen to somebody, and you want to understand something, you cannot request every second package of data for a second time. That would take that too long. So therefore, continuous stream is required, and we need continuous power supply. We could use batteries in cases where the data exchange rate is relatively low and where the stimulation frequency is relatively low. So cardiac pacemaker, for example, let's say it lasts for 5 years. Let's take an example of 10 years, then it's easier to calculate by heart. And we have a stimulation rate of, let's say, 60 beats per minute. That's 1 per second. Right? If we would have a cochlear implant where we would probably need 300 Hertz, that's a factor of 300. Now let's divide 10 years. That's 1,200 a month by 300. That's 1,200, 2 zeros off makes 12, divided by 3 makes 4 months. An implant that lasts for a month, which you need for your whole lifetime, is probably not a good idea. And if you would now come with the idea, hey, you take a primary battery, let's take a rechargeable one, then we go for 1,000 charging cycles, and then we are no longer that sure if the battery would work or not. So rechargeable battery does seem to be an alternative, but we have to check out how good does it work. And with that, we come to the point where we say, hey, battery is no option. So we need continuous energy supply, or at least something that allows us for charging something and having the option of recharging over the envisioned lifetime, right? And therefore the idea came, why not using inductive powering that you use from your electronic toothbrush, for example. Batteries are getting better. Probably we can come one day to a rechargeable implant that lasts 20, 30 years. The question always is about the safety and the reliability. Should that work for a vital function like a cardiac pacemaker, or is this something that improves quality of life only? Yeah, if it's only quality of life, we can have a certain margin of reliability. This margin gets really small if it comes to vital function that decide on life or death. So that's the motivation behind that a little bit. Cochlear implant is one option where that continuous data stream is needed due to the high stimulation frequency. Another one where I was involved now 23, 4, 5 years ago was an implant for stance and gait that did not work that well at the very end with respect to daily use. But in that case, we had currents up to 30 milliamps over about 10 channels. There were some other channels with nerve electrodes that only needed 4 milliamps. And that would mean you really drain your battery also within weeks, if not within days, with that high amount of current. So how should that work? We need an external controller, and we have an implanted device with whatever control electronics that goes to the end effectors, either for recording or for stimulation. And that coupling is done inductively, that means in the near field, and therefore the outside coil and the inside coil need to be close. That might be a disadvantage with a coupling. That is an advantage with respect to safety, security, privacy. So if you need the direct coupling, direct means within 2-3 centimeters, it's more difficult to hack the implant with something from a further distance. If that would be radio frequency from wherever, then you would definitely have to take more care on encryption. Nowadays, encryption is also done on those inductive coupling, that you have a kind of system where a certain serial number or ID is requested, and then a certain encryption starts. And if we already have that connection for energy supply, can we use that for data transmission? That's the question. And we will see that there are some limitations, and we could also use different channels. Ultrasound is under discussion, light is under discussion, but we always have the trade-off between, let's say, simplicity, complexity, and the power needs that we have. And there are good reasons for certain applications to have multiple channels, and there are other good reasons that we have one channel only for others. So, just to get an idea, who have had courses on inductive coupling, telemetry, data transmission in the bachelor program? Maxwell's equation, Biot-Savart. You don't get a grade on that, just yeah. So a little bit is there. So you don't mind if I repeat that? No? All right. Because some years there were persons, I just had recently, and I could go faster and tell other stories. But if you didn't have that, I take my time. So the objective here can be summarized in those sentences. So first of all, we have to create a magnetic field. We have to transmit energy over that magnetic field, and we have to receive that. That means there's a transmitter, a receiver, and something in between. That's our body. And we have to see how to get that in. There's a side question: does that hurt? Yeah. Are there side effects? Yeah. That I have to consider. and how to get that, and is there something I should consider? There's always a trade-off between energy, distance, data rate, things like that. And we could describe everything in electromagnetism with the laws of Maxwell. They're very complete. They couple electrical and magnetical fields, and they are a pain in the neck, because you would have to solve three-dimensional integrals of whatever equations with vectors and tensors and things you don't want to use just to get a rough estimation if something could work or not. But if you like, you could go to that set of those 4 equations, and everything is covered there. But I think it's better, for the sake of understanding, if we cook that down into more simple equations that are, of course, a bit limiting there. Sorry. With some limitations, but limitations that we already have in the human body and in some other constraints there. So first of all, we simplify. We take air as a first step and just play some tricks why body is close to air. We have stationary conditions. That would mean we do not switch things on or off. We take it for granted that they run. That means all those phenomena that we get when switching something off or switching off is blanked out for simplicity reasons. And we arrange everything in a way that we can calculate things in a linear manner. That helps us a lot if we can take linear equations instead of nonlinear ones. So, the basics of everything here is the magnetic induction. That means if we have a current that flows somewhere, let's assume we take a wire, but it could also be a plate or whatever, but let's take a wire first. We have a wire, and it's straight. Straight wire is it's easier to calculate, and the current flows in there. Then the current which flows through the wire creates a magnetic field, B. And if you take your right hand, that's very important, drop your pen. If you're not a left-hander, take your right hand, otherwise you have wrong signs there. And your fingers point in the direction of the magnetic field. Yeah? Technical current flow, so from plus to minus, fingers point in the direction of the magnetic field. And the equation there shows us that the current I is in the numerator, and the distance A from the conductor is in the denominator. That means the further distant, and the 2 pi is just the 2 pi A is the circumference. Mu 0 times mu r is a magnetic property of permeability, and we take air, then mu r is 1. So easy. What we can say is the stronger the current, the stronger the magnetic field, and the further distance we are, 1 over A, the smaller it is. So that's important. It's not very pleasant because we want to transmit something, and the further we go, the smaller it is. So one constraint. And we should not overdo it with the current. How can we now focus that magnetic field? That we don't have all those rings, but more something linear that goes with maximum force, let's say, in one direction. And the idea is to make a coil of a helical bound conductor. And if you have some time, imagine a coil and take your right hand and look with your fingers where the magnetic field lines go. And if we do that, we find out that they get focused in the inner side of the coil, and they're less dense on the outside. That means binding a helical coil helps us to focus the magnetic field in the inner side and a little bit to the left and the right. And the number of turns over a certain distance, capital N over D, D is the distance in length, gives us a proportionality to the magnetic flux, the magnetic field. That means the more turns I have, the stronger the field is. The more turns I have, the longer the coil gets, and it's no longer handy. If you imagine you would have to transmit something and you would have to place a long coil on your head or whatever, it's neither nice nor handy. Yeah, so that gives us already another constraint. So we want to have coils, they should be strong, but they should have a flat geometry. That's another constraint here that we have to take into account later on. So the permeability, this is something from the early days, 200, 300 years ago, where people did not talk to each other as today. So there was a kind of wrong assignment of terms to the different letters. So we have the magnetic field H and the magnetic inductance B, and if you compare that to the electrical field, that is equivalent to E and D. There, and we always look for equivalences in physics, that we are able to somehow understand and transfer processes from different circumstances and find more overarching laws for them.
One question?
Yeah.
So the field that gets induced by a current is not the B field but the H field?
It's the B field.
That's
the
magnetic induction field.
Yeah, right.
And what is then the magnetic field?
It's the induction divided by mu.
All right.
So that's the mean thing. So if you look on that, then you would say, well, B is more the E and H is more the D.
I don't anymore.
I
don't know anymore what D is.
So D is the electrical field times the permittivity. So the electrical characteristics of whatever insulator or material you have in between.
Okay.
So let's take the induction as the thing that gets induced.
All right.
If we would then blank out the mu, then you could say, we also find the H there. But let's take it that way. That helps us better in the whole story, not to make some logical breaks in there.
Okay.
So we can say that one is mu dependent and one is not mu dependent.
Yeah, right. So H is not mu dependent, B is, and mu is something that helps to strengthen the magnetic field. And you might have seen those pictures with kind of compass needles that get aligned, and you cannot align them more than all in one direction. That means we have a kind of saturation if we have a material that we cannot magnetize that material up more than to its maximum. And therefore that means you could increase the H then, but the B is saturating. But that goes far beyond my intention here. All right. For our applications here in, let's say, medical telemetry, we are talking about short coils. And this is again one of those things from practical application. I mean, what is a short coil, right? What is a long one? What is a short one? Is a short one always a short one? Things like that. And this is a lot of persons did a lot of very sophisticated calculations and made their mind and had strong discussions about that. And we can say if the diameter, the thickness of the coil is much smaller than the radius of the coil, then we have a short coil, and we should also take the wavelength of the electromagnetic waves into account. That's the lambda here. If the distance that we consider is smaller, distance here is the x-axis, is smaller than the wavelength over 2 pi, then we are in that range where it works. That means if I'm right, for our frequencies that we're taking into account, there's some centimeters or something like that. That's good enough. And as we see here in that sketch, the field in the center and along the x-axis is homogeneous over a certain distance, so we can take it linear, kind of. If we go further apart, then the field lines spread and things are completely different. So, as an example, I did not calculate the x, that's a pity. So if we have a radius of 3 centimeters of a coil, that means the diameter is 6 centimeters, and we have a thickness d of 5 millimeters, then we can say, well, 5 millimeters is much smaller than 3 centimeters. And we have 300 megahertz. Can I do that by heart? Frequency times wavelength is speed of light. So 3 to the power of 8 divided by 3 to the power of 8 is 1. Well, that's an easy one. Huh? So we have x smaller than 1. Well, that would be 1 meter divided by 2 is 50 centimeters divided by 3 point something. Around 10 centimeters. Right? If we take 10 centimeters, we're not that bad. That means up to 10 centimeters, it could be a good distance. In most cases, I can tell you, we have much less than 10 centimeters for the reason that the human tissue is not air. Well, we have water. Whatever we have, there's water in there. And the water, the epsilon r of water is about 80. So the permittivity, and that would mean that we have quite some attenuation of the electric field. And there are tables where you can find out if I have that frequency, what is the penetration depth into the tissue. So by that, this boundary condition of a short coil is always, let's say, the best possible case, and in reality, due to our tissue and all that stuff, we are limited by the attenuation and not by the boundary condition of coil design. That doesn't make life simpler, but it helps us that we are on the safe side with the coil design. So, on top of that magnetic induction comes the magnetic flux, and that is a kind of thought experiment where we say, well, if we have those magnetic field, and a field is always associated with the imagination of field lines, can we calculate the number of field lines in a given area? So the field lines penetrate cross-sectional plane, and this magnetic flux phi is a measure how many field lines do penetrate that area A. This helps us to if we have a large coil and a smaller coil, to check how much goes through the smaller coil. Yeah? And if I have a displacement of the coils, does that matter or not? Yeah, a little bit, probably not, but if I would tilt one of the coil or the other, the field lines are no longer that straight, and that means if I have a tilted area, I have to take the cosine depending on the the angle, because if the second coil would be orthogonal, 90 degrees to the first one, and we assume that magnetic field lines go straight, we would have no penetration no matter how large the area is because of the orientation. That means we always assume in our linearity approximation that those planes are parallel. If not, we can correct with the cosine of the displacement angle. If I have more than one turn in a coil, I could say each turn of the coil experiences once the magnetic flux. If I have two turns in series, they both see that magnetic flux and the influence should be probably added. That is the idea with the magnetic potential here. That is the sum of the flux, and that would mean the magnetic potential goes up linearly with the number of turns that I have in one coil. At the end, the question always is, what is that good for in my application? In fundamental science, everything is good for everything, and you gain knowledge like crazy. But if you want to design something, you should always have your goal in mind. So what do I want to do, and is this knowledge that is needed for that, or is that something that is good to know but completely useless for that application? So far, we have talked about the magnetic field. At the end of the day, the question is, how do I power my electric circuitry inside the implant? And for powering, I would need voltage and current. Electrical power, P, is the product of the voltage times the current. That will mean we need some effects, and they are hidden in the Maxwell's equations, to get voltage and or current out of the field that I have. And this is done by Faraday's law of induction. So if we have a voltage, if a voltage is induced within a conductive loop, this is done, well, if was wrong there, a voltage is induced if a temporal change in the magnetic potential occurs that penetrates that loop. So on the primary side, we have a current flowing somewhere making a magnetic field, and then we have the secondary side, and I have a loop. And if the magnetic field changes over time, then I'll get an induced voltage. Important, that is voltage, induced voltage here. That means we have dC over dt, and that means we take the number of turns in a coil that we have and look for the change of the magnetic potential phi, the magnetic flux phi over time. So d phi over dt. That means if we have linear arrangements, blah blah, so all the approximations, that phi was b times a. So what we can take is, what you can do is making brackets around b times a and differentiate that. If we differentiate that, please remember we have to take the product rule. That means we have to take one parameter out, make the deviation of the other parameter, and then do the other thing for the second one. That means we have here the number of turns in a coil, and it's either the magnetic induction multiplied with the change of the area over time, and the area multiplied with the change of the magnetic induction over time. And this means we can either change the area. That's probably not good for a coil, you know. If a person has to wiggle around with that coil, probably not good. Huh? So that means we should have a changing magnetic field. On the other hand, that means if we need a voltage induction outside of the context of medical implants, I can have a constant magnetic field and change the area. That is, for example, a generator. Yeah, you have two magnets, you put a coil in and you turn it around. That's what some of you might have on your bicycle. So the dynamo that is there, for example, in the wheel, in the hub, turns around, and there's a magnetic field by permanent magnets, and then you turn some coils around, and you get induced voltage that you can use. The basic principle of electrical generators. You can do it more sophisticated, and then we end up in electrical cars or something like that. So that is the part that is now became very, very important and exciting over the last years. Yes, please.
Can you go any of the number of turns of the coil?
We can increase the number of turns in the coils, but then we have to check out if this is helpful with the length. Yeah, if we have too many of them, then it's hard to handle it. So it's always a kind of trade-off with the number of turns and what we get there.
One question maybe.
Yeah.
What does it mean that a voltage gets induced? Because with current it's like kind of easy to imagine, but voltage. I mean, you need to separate charges then, right?
Yeah, you get a voltage, and when you get a voltage, we can imagine that as separated charge.
Yeah.
And if a current flows, the charge goes somewhere, right? And if this charge goes somewhere, the voltage might get smaller because the number of charge particles gets less. And therefore I said it's important to differentiate that, because if you need a certain current to drive something, that relations should be such that the voltage does not break down. So you have to take care at the end to check out, is my power source that drives the primary coil strong enough to do that even when the secondary coil needs energy. And I'll show that to you later. You can use that side effect, that changes in resistance change the current flow. And if the current flow changes, you have a change in the related voltage. And that is seen even if your microcontroller switch on or off something in the implant, that can be seen on the powering side. And you can either have to control that and regulate the transmitting power, or you can use that side effect as feature and modulate on your implant side the current or the impedance, and thereby transmit data backwards without having an active transmitter there. So it's a kind of passive back telemetry.
Okay.
So you should separate that first. It's all related together, but I think it's good for the concepts first to separate that and see then in a second step what does that mean if it comes together.
Because I thought the separation of charge is basically flowing charge, so it's in some sense current, but it's like it doesn't flow off. So
No.
Okay.
In the first step, you have it in an open circuit.
Okay, yeah.
Yeah, you have it in an open circuit, and that open circuit generates that charge separation and the voltage. And this goes all beyond those slides, but normally if you have that, you can say, well, that magnetic field causes an electrical field due to the voltage. Then you have the gradient of the electrical field comes with a voltage, so another Maxwell equation. And this change causes then a magnetic field again. Change of electrical field causes a magnetic field. that is superimposed in the opposite direction of the original magnetic field.
Okay, and that you can theoretically measure and then you have to say, okay.
And that stuff in our frequency ranges, that's all negligible. But if you go to higher frequencies, for example, something occurs like the skin effect, that this superposition leads to effects that the core of a conductor is field free and no current flows through the core of a conductor, but only on the surface, on the skin. Therefore, it's called the skin effect. This has been, for example, used or is used in high power transmission, that you make cables with a no core, but you use that core to cool the rest of the cable.
Okay.
So it really goes into many details, but that was an important question. We talk about that in open circuit. And you can also measure by that the magnetic field by yourself relatively easily. If you take a loop of whatever conductor and put it into the input of an oscilloscope with a very high input impedance, where no current flows, and then you go around in the room, and if you see some voltage somewhere, you know that magnetic flux is coming from that direction. Sometimes done if you have interferences in your system and you have no idea where they come from, that you use that frame antenna and check out where does the flux come from, certain orientation or something like that.
Okay.
Good. If we have those coils, I think we can all admit that we tend to be a bit lazy. So we don't want to solve differential equations. We don't want to solve integrals. We want to have something relatively easy where we can bring the material properties together that give us an estimation how things work. And that is the resistance. Normally, that's what we use for current to voltage. If we have alternating current and have those magnetic fields, then we should take the inductance. That is the equivalent material parameter to describe coils. And that means we bring everything in there as the resistance R is the ratio of voltage over current. Here, the inductance is the ratio of that magnetic potential over the flowing current. And then we take the equations that are introduced and find out that this is the number of turns times the material property of the material, the magnetic material property, so the mu, times the magnetic field times the cross-sectional area. And by that we find out that this L, if we take H as the current, the conductor, right-hand rule, I over 2 pi A, and if we do everything together, then we come with that equation here for the inductance of a loop. I could now introduce many fantastic laws that describe everything in the latest detail, but I skip all that and want to come more to something that we all can imagine easily, that's more important for applications. So if we have one coil that acts as transmitter, let's say the left-hand side loop, and we have a receiver, the right-hand side loop, it would be nice to describe how does the coil on the left-hand side influences the transmission. What properties do I have on the transmission side? What properties do I have on the receiver side? And how do those coils influence each other? So if I don't have an open circuit, that's something that should be driven. How does one side influence the other side? And that description, how does one side influence the other side, is called the mutual inductance M. And in the best of all worlds, M12 is equal to M21, so that we have a symmetric arrangement. That is taken also as one of the simplifications. And that would mean if I have a magnetic potential on the secondary side, and I look on my current on the primary side that flows to generate the field, how does that secondary side influence my primary side? And that is the idea that the current which flows here on the primary side creates a magnetic field that influences something here on the secondary side, and not only on the primary side. And looking on that, it's not really very pleasant, because we have an integral where we have to go over a certain surface, A, and we have to integrate that over the surface. Yeah?
Is that equation for the mutual inductance true for only this orientation, or also
For all orientations, since we have that area integral, and depending how your area is, you have to integrate in a different manner over that area. That covers then the orientation of the coils. Since we normally are not that pleased in doing those integrations, persons came up with a more simple parameter, the coupling coefficient. Unfortunately, this is a kind of circular definition. You get the coupling coefficient if you have the mutual inductance, and you get the mutual inductance if you have the coupling coefficient. If you don't have one or the other, you're kind of lost. But the coupling coefficient is more taken by most of the persons as a qualitative measure, independent from geometric dimensions. So how do coils couple into each other? And if you go into design books, they give you some hints when the coupling coefficient is smaller than 0.5. Take that equation. In reality, we have the coupling in the percent range. So, and I don't mean 90, but rather 10 or 20% or something like that. And that means we need a lot of energy on one side to get something done on the other side. How does that look like? More in practice. We have a primary side always on the left hand. This is the transmitter, extracorporeal, and the receiver is intracorporeal. And we need to transmit energy in one direction and data probably in both directions. Depends what we want to do. If we look on that circuit diagram, we find out that we have a series resonance here on the primary side. So C and L make an oscillatory circuit. And they are in series, while we have C and L in parallel on the secondary side. Also an oscillatory circuit, that means they want to oscillate at a certain frequency. Since we have real worlds, we also have resistors in here. So it's not like a resonance catastrophe. Here we always have some resistors there. The RL at the very end on the secondary side, very right, is the load resistance. That is what we like to drive. That could be, don't know, if you want to measure the temperature, then it's a thermometer, so resistor or something like that. If you want to measure the pressure, it's probably a capacitor. It could be also the output of a digital circuit there that you use for whatever. In best cases, you want to transmit something backwards, and there are different options how to do that. There's this third option that is not shown here, and that is an active transmitter from the intracorporeal side to the extracorporeal side. That could be that you use that circuitry for powering only, and then power an active transmitter that sends out the data. And there are, certain opinions about that, when to use that and how to do that. So the extra corporeal part is in series resistance to maximize the current to drive the coil. If we have resonance, the imaginary part of the transfer function goes to 0. That means omega L is equal to 1 over omega C, and that makes the resonance at 1 over the square root of LC times 2p, 2 pi. The good thing is, even though we have a slightly different equation for the parallel circuitry, the resonance frequency is at the same frequency here. So the equation is the same for the resonance, independent of its series or parallel resistance. In parallel resistance, you maximize the voltage, and that helps to drive the circuit. And this is kind of standard, that we have series resistance, series resonance on the extracorporeal side, and parallel resonance in the implant. What we want to get is best possible transmission of energy. Now, we don't need too much from the outside to drive the inside. And therefore, there is a quality factor Q around, while we have to adapt L and C and R in a way that we get best possible energy storage in the inductor or capacitor over the Joule's heat that we generate. And since this is not 100%, but less, that means that we generate heat. And generating heat into the human body is not that ideal. As disease, this is fever, right? And you know that from cooking, if you generate enough heat, you cook your meat, and proteins denaturate over 40 degrees C. And therefore, there's an international standard that whatever kind of energy transmission or activation of an electronic circuitry must not increase the average temperature for more than 1 Kelvin. That is not that much if you drive continuously an electronic circuit. You can take advantage of the bloodstream inside the body. Then you have to prove that the bloodstream helps you to carry away the heat. But this is sometimes a real showstopper, since you get very easily 10, 20, 30 Kelvin more in electronic circuits, and over time you have to check out that this is staying inside that limit of increasing the temperature inside the body. So what is now the correct frequency? This is still a question where people can discuss over ages, because the correct frequency is always a trade-off between the physical requirements and your application requirements. If you need 1 data per minute, battery status of a cardiac pacemaker, you don't want to have that in a millisecond range. Once a day is probably enough. Then you could use a slow frequency. With a low frequency, you have the advantage it penetrates better your titanium package wall, it penetrates better the tissue, but you get less data out. If you have higher frequencies, you get more data out, but they do not penetrate that deeply into the tissue. And there's an international commission which takes care which bands can be used, which bands should be used. I mean, if you communicate with your smartphone, in most cases it's wouldn't be that important if the sound quality is a bit less, right? If you drive medical devices, you should be safe on that side that you can get the data rate you need to get. There are certain laws and regulations that you can try out in research and development, certain frequencies, without asking for allowance.
All the frequencies that are used by submarines or the military also known, or it is not in
Yeah, the question was, are those frequencies known that are free or not? And in general, they are known. So that ISM band, industrial, scientific, medical, there you have certain frequencies on which you are allowed to operate. But you do not know how many others are also selecting exactly that frequency when you design a device. That means it could happen under certain circumstances if, whatever, there is an assembly of cochlear implant carriers somewhere, and they all running on the same frequency band. I mean, if it's purely inductive, then they're all in their vicinity, then it's fine. If you would have some RF far field communication, then it could get a bit tight. And the ISM band was invented, I don't know, 20 years ago, something like that, when there was a push on devices with telemetry. Before that, let's say up to 1990 or something like that, those devices were more or less ignorant of each other. You had radio transmission, television transmission, and radar and stuff like that. And you could look that up, and some people did look it up, and they were on the lucky side, and others didn't look it up. So my favorite example is one nice implant, the Bion, that I showed you from the packaging side, where that guy who invented that or who designed that forgot to ask or forgot to check it out. And it's not really funny, but it's a bit weird because this institute or that foundation is sitting in an old building that was originally built from a military company on secret radar transmission. So you have it's completely electromagnetically shielded, that building. The outer walls are made. I was there this spring visiting that institute, and it's made out of tiles that are electromagnetically shielding. That means they have everywhere inside the building repeater stations that you can use your mobile and that you can use the internet and whatever. And this guy was developing that medical device inside that building from old military heritage days, and forgot to check out the military transmission frequencies. And he was in the middle of an emergency frequency of the US Air Force. And they were, of course, not happy to sell that frequency. And there was a lawsuit of about 20 years or something like that. At the end, this guy won, so they are now allowed to use that frequency, but they no longer develop those medical devices.
Can't you just change the frequency? Or isn't that so
easy? You question, can you change the frequency? Yeah, you could. In that case, it was a device with a diameter of 2 millimeters and a length of 10 millimeters. And they had designed the whole device with a number of turns of coils and whatever, on that frequency range, and to change from, let's say, 10 megahertz to 300 megahertz, that would have been a major design change, coming with size changes, and then I think those were the days where they already had ordered for a fortune hundreds of integrated circuits, very customized for their frequency and whatever. And I think they thought it would be easier to get that frequency. I think it would have been cheaper to redesign the whole device instead of going into that lawsuit. But this is something that could happen. There's another device, and I forgot which one it was designed in the US, and when they tried to enter the European market, they found out that this is the television transmission frequency of the Tour de France. They have a reserved bandwidth for those sports events, and they were in the middle of that. So that is for me. Luckily, I'm not in that. I'm not the frequency person in developing telemetric medical devices. But I think this is really an issue to find out where can I use that, where am I safe. It's now all good with that ISM frequencies, so you could check out who's there. There are web pages where you could check that out, but before that came up was difficult, and I'll tell you that story, that you keep that in mind to check out who else is working on that frequency. Is it a good idea, or should I hop to another one? You might know that from your Wi-Fi server at home, where you can either have an automatic bandwidth hopping, or you can, if you know your iPhone of your flatmate is always on that frequency, that you do a hard assignment on your mobile to another frequency band that is available to get more and more bandwidth for transmission. This is something that is good, keeping that in mind. There, and it depends which region you are. You know, this is something you should keep in mind. Which region do I want to cover? Are there some specialties there? As I said, there's,
These TSM, what do they call TSM? Yeah,
ISM.
bands, are they internationally free for all?
ISM bands are international. It's an international standard, which means you should check up if the US has their own standards and if they comply with the international standards. So we have the International Standardization Organization, ISO, and some things are still running on the military standards and the ASTM. So military standard is MIL, M-I-L. MIL standard 883 for temperature cycling. I don't know if it's still transferred into ISO or not, but it's used worldwide. And there are some ASTM, American Standardization, blah blah, measurement. They're also not yet in ISO. I think it took 25 years to get the MR compatibility from ASTM into ISO. So that means, yes, it's international, but it's safer to check the US standards. So, now we know where we are allowed to transmit. Now we have to check in the second step, is this good for us? We have limits of continuous exposure, that you don't grill yourself or your neighbor. And that means the temperature increase must be below 1 degree centigrade or Kelvin. And the legal body is the International Commission on Non-Ionizing Radiation Protection, ICNIRP. And you can Google that. There are not so many wrong hits if you have ICNIRP. And then you find all the actual numbers there for free. And there are current densities depending on the body rate and the specific absorption rate. unfortunately, legal bodies of different national countries could not agree on a worldwide standardized method on specific absorption rate. That means if you want to put that into different national entities, you check out what is meant by the specific absorption rate in that particular country. There are 2 or 3 definitions worldwide that vary a bit. I mean, normally it should be the energy per kilogram body weight, but the question, how do I calculate the energy, is different. Good. That means we have to check that out. And the question now is, if we know all of that, and we are still keen on developing things like that, how do the electrical circuits or the electronic circuits look like? And this is now all stolen from Wikipedia. So we have primary coil drivers. That's the primary side, extracorporeal. And if you look them up, you find classifications A, B, C, D, E. Normally, it's sometimes limited to class A and class D, and that does not mean analog and digital. Yeah, sometimes people think, well, A is always AD, converters is analog digital. Here, it's just the alphabet. Yeah, it's just the alphabet, A, B, C, D, E. Class A are linear, harmonic, low degree of efficiency. And class B are linear, harmonic, push-pull output. That means they go up and down. And also have little distortion, also for audio amplifiers. That means the positive side is they are linear, the negative side is they have low efficiency. Class C, linear, harmonic, working in resonance, high degree of efficiency, high distortion. Distortion means that you have frequencies of higher order of your resonance frequency on top of that. That's in audio, that's a distortion factor. You take the sum of all higher harmonics over the basic harmonic, and then you get your distortion factor. And we have class D and E. They are switching amplifiers. They are highly efficient, and they have high distortion. That means even if they might look like a sinusoidal wave, so it goes at least up and down, and it's not a sawtooth, but has some round edges, it's not harmonic. That means it's not one sinus, but something different. So my favorite, or one of the favorites, is a class D driver, and I want to dig into class D and class E drivers here. That's a switching amplifier where you take 2 transistors, field effect transistors, metal oxide semiconductor field effect transistors, that's the MOSFET. And they are one PMOS and one NMOS, and that means while one transistor is conducting, the other is not conducting, and the other way around. And by switching them, they always, if you switch them, that means if you put the rectangular current here on the input, they open close, and in those transitions, they let the current pass. The current goes over a capacitor and an inductor, and here a resistor, and that means we have a resonance circuitry here, and by switching, if you do that in the right frequency, you kick your resonance frequency, and thereby you get a good resonance, and that resonance then is transmitted over the coils. But it's not really, and the LC tries to make it harmonic, but it's not really. So they try its best, but it's always kicked then by the switch. You have a question?
Is this inductance L the transmitting inductance
Yeah. So it's the transmitting inductance. Probably you have a different inductance if you need to tune it a little bit. Yeah, and the R is induced, the resistor here, to get an idea how much voltage do I get on the primary side. And with that, you have losses during switching only, since you have no current flow if there's no switching thing. Yeah, and that means in ideal case we have no losses when no switching is done, but the higher the frequency, the more losses we have. And the degree of efficiency is over 90%. So that is really cool. Which doesn't mean that it does not get warm, just means that a lot of stuff is transmitted. Very fascinating to me, since I have no idea who came to that idea to make it that way, is the Class E amplifier with ideal efficiencies to 95, 97, 98% even. That means it's very efficient. With the idea, I have only one transistor here, and if I switch that, it's either open, so it's short circuit, then I have no voltage, or it's closed, then I have no current. And if the power is the product of voltage of current, and either one or the other is zero, then it's zero. But there's a current flow if I go from open to close or from close to open. And in that transition period, I have those power losses. But you need to have an optimal working point there, that it always switches in the right point of time to drive that resonance, and therefore you need a control circuitry that's not sketched out here. So there's a control circuitry which tells you when to use that switch on the gate of the MOSFET here to drive that transistor. But my colleagues from microelectronics told me that's easy. And I always get suspicious if somebody tells me it's very easy. Then there are some tricks there. So we're now at the point where we know we can transmit energy. And the question is, and we have a kind of sinusoidal wave or oscillation. The question now is, how do I get data on that? And it should work, because we still have AM and FM radio, so we can switch on our radio and we get something out that we probably not always like, but there's music, there's voice, and we can clearly understand that. So how to get those data on those oscillations? That's called the encoding, and this is here probably not politically correct, that example here. So if I have a fire and I see the smoke, then I just know there's a fire. But if I want to transmit data, I have to somehow interrupt the data stream or interrupt the stream to get data out of that. And the receiver must know the code of the transmitter, otherwise that doesn't work out. So if some person sends something and the receiver does not know what it is, you can just say, oh, there is somebody doing something, yeah, but you don't know what it is. And we are here on the syntactic level only. Nothing about semantics or semiotics. That's really syntactic. How do we generate letters? Could be probably good to have two different values, and if I have only two different values, I'm in digital encoding. I want to skip all the old analog schemes. So the more I send, the more it is. So that's analog coding. that works, but it's more difficult. Therefore, I go to the digital one that is easier to understand. I want to transmit ones and zeros, and the coding is then into the language of the ones and zeros. And we're talking here about the sine wave, about near field and inductive coupling. So there are different options if we go to different modulations. And very important in your back of your mind, we need to power our implant. That means the amount of energy that I transmit should be independent of the type of information. Yeah? If I tell you something, your energy of understanding that, or my energy of speaking that out, should be always constant, independent of the meaning of that word. We all know that if I listen to a philosophy lecture, I need more energy. Yeah? But normally it shouldn't be like that. You know, the power of receiving something should be independent of the information that I transmit. So what can I do? I can do amplitude shift keying. That means I switch between two values of the amplitude. And this, I know, this is a violation of the sentence I said just some seconds before. The worst thing is if you switch between off and on. Yeah? Because you do not know if something is zero or just switched off. How should I detect if I have that, two values, and one value is zero, if switching off is nothing or zero? Yeah? Therefore, it could be two values having something switched on and off. Here it's on and zero. That doesn't make so much sense if you want to drive something somewhere, because that's something that implant needs continuous energy. But this is an easy way to understand this example here, to understand amplitude shift keying. So two values, 1 and 0. Another thing could be phase shift keying. That means I have a wave, and then I make a break and turn the phase by 180 degrees. And this is then a 1 or a 0. And this is indeed one of those modulation schemes that is hard to imagine how you detect that, how you do that, but this is one of the most efficient ones that is even brought to higher levels with more options to code more on a single wave. And the third one, from a general principle, is frequency shift keying. So you have two different frequencies. One frequency codes a 0 and another frequency codes a 1. That sounds very good, but comes with a challenge. If you tune a transmission system on its resonance frequency and then you use frequency shift keying, then at least one of the frequencies that you use are out of resonance. Or both. That would be even worse. If you say I take the middle frequency and one frequency is left from that and one is right from that, that could work under certain circumstances, but we have to take care how to do that. That we still have a good, efficient transmission between the coils. So that is the ones and the zeros.
Maybe I have a question.
Sure.
What is the resonance frequency for such a circuit? Like, how can you imagine?
We had it on the slides before, very early on. Okay. So 1 over the square root of LC is the resonance frequency.
But is it just working the best in that frequency?
Yeah. It's like resonance, you know, from Yeah.
node from, I don't know, materials. that
Yeah,
is-
right. It's the same for electrical circuits, that resonance. If you take certain values and you would put in repetitively a little bit of energy, then this circuit would resonate at a certain resonance frequency, like a ruler or a string on a guitar or on a violin or something like that.
Okay, so basically you want that frequency because you need less energy.
You need less energy and you get the best power output out of that.
Alright.
Question in the back?
Does it then mean like it resonates with different frequencies as well, but not as good?
Right. You can drive it, but it needs more energy if you're out of the resonance frequency.
And do you need to apply then, I don't know, some filtering? Because otherwise you might get like from other sources than intended.
A good question. Do you need a filter for that? It's that resonance tuning on the parameters of the inductor and the capacitor is already a kind of filter. That means if somebody would try to activate or to excite your circuitry at a different frequency, it would get a very small response, while you get a huge response if you are in the resonance. And that means if you just think about output versus input, you get a kind of attenuation if you're out of your resonance, and you get no or little attenuation if you are inside your resonance. And therefore it's a kind of self-selective. If you are on the right frequency, then you get good transmission. If you are off, you get attenuated and it doesn't disturb. And therefore, that frequency shift keying is a kind of tricky. You want to design your whole system that it really sticks to your resonance, that you only get what you want to get. But if you now take a coding to transmit data that are a little bit left and right from that resonance, you don't get it as good. One option could be that you make your resonance characteristics more flat, that you are, if you are left and right, still on a good transmission rate, but that would come with a side effect and disadvantage that distortion sources would also be able to get more of their stuff in there. And this is then the balance, and the trade-off, which you have to design. Two things that I want to share with you before I close today is once the load shift keying. So the question, can I get information out of an implant without having a transmitter in there? Just by the regular coupling of all the components. And this is called the load shift keying. That means I change the load by, for example, putting a short circuit in here. If I put in a short circuit, my mutual inductance of the secondary circuit will change, and you can monitor that in a change of the current in the primary circuit. And that is shown here. If I close the switch, right-hand side graph, I see an increase of the current on the primary side, even though this switch was closed on the secondary side. And if I do that in a proper manner over time, I can transmit data then. The question still is, how do I know that this is data and not a disturbance? And that comes then with a coding. Yeah, like the question, is nothing a zero or switched off? And that means we have to go to certain coding strategies. We should have the possibility to transmit data on every modulation cycle. And we should include start, stop information, probably a clock. In a way, they say, well, my data comes every clock cycle. And we should also include safety features. That could be that a word is 64 bits long, and then comes another word that gives me the checksum of the previous bit, or I have the checksum in the first bit of a word, that I know if it can work or not. That's similar with your IBAN of your bank account. Yeah, if you do something wrong, they say it cannot work, because there are some numbers in that give you the checksum for the rest. So that is important to know if your data that you receive and decode, that you know this can be an intact word or this is a corrupted word. Because if it's corrupted, then you could send out a request to resend that word again. Yeah, there should be then, everything should match the application, and probably it's good to have some synchronization features if things run out of order, that you can bring them together again. One example, I would say the most prominent one for commercial coding in those medical device data is the Manchester code. Comes with the advantage that you have the information not in the level, so it's not high is 1 and low is 0, but in the transition. If you go from high to low, this is a logical 0, and if you go from low to high, this is a logical 1. And that means the step function or the integral under the steps for a 1 and a 0 are equal. So it doesn't matter if you send a 0 or a 1, you still have the same amount of energy. And you can use a violation of that code as information, oh, please listen, I'm going to talk. Yeah, so if you have, for example, here a so-called preamble, then you have 1, 2, 3, 4, 5, 6, 7, 8 steps. So the system can wake up, and then you have a violation of the code for cycles 0, 4 cycles high. That shouldn't work, since we always talk about transitions, but that is a violation of the code intended to tell, now I'm going to send data. Then the data come, low, high, high, low, high, low, high, low, low, high, whatever. And then at the end there's again a violation of the code, the other way around, to show this is now the end of data. Question?
If I want 2 ones in the data following on each other, how do I do that? Because
2 ones are low, high,
but I have to get from high to low first. I can't go low, high if I don't go high, low in between.
Yeah, but that transition here from low to high.
Yeah. But I have another transition from high to low.
Yeah,
first.
but that 2 are 1 bit.
Okay.
Yeah,
Yeah.
two,
Okay.
2 cycles.
Yeah. Okay.
2 cycles are 1 bit.
All right.
You're right. If it would be just 1 bit, then it wouldn't work.
Yeah. Okay.
Yeah, but 2 slices
Yeah.
are 1 bit.
Okay.
That means if you would, you could then have either high low for one, low high low for one. Yeah, if you have different ones, or the same step, then it's 1 1. Disadvantage is that you need more, let's say, slices for data. If you would say low is 0 and high is 1, you could have twice the amount of data, but with the drawback that you have information-dependent energy transfer. And believe me, there are so many proprietary codes where people say, I don't take the Manchester, that takes too much time, and then you invent something different, which doesn't matter that much if you just do that for yourself. But if you think about intraoperability between devices, then it's a benefit to have a generalized code where whatever receiver station could talk to transmitter station. Yeah. Imagine each company would have different codes for wireless LAN routers. That would be a nightmare if you would have to write your own decoding program or have whatever program that decodes then, and if you go into another room, you need another app to get that decoding. Therefore, that standardization is really very important for interoperability of devices. Yeah, I'm at the end of topic and time. So here are some references to the ICNIRP. The back telemetry is taken from an old Donaldson paper. And I'm still a great fan in the English language of the Horowitz and Hill, The Art of Electronics. This is a book of shared knowledge where you can take whatever you like for filters, for amplifiers, for whatever can be made out of electronic components, and it works. In German, that's the Tietze Schenk Halbleiterschaltungstechnik. That's another iconic book where you can take the circuits there, you put them on a breadboard and they work. The Art of Electronics is more pleasant to read from the style. Yeah, that's the literature side. And here the take-home message, always meaning this is what you should learn and keep in mind. So inductive coupling is an adequate method for energy supply and data transmission. Efficiency depends on the circuitry. And the transmission has to be chosen according to international standards and your needs that you have for the particular application. With that, I'm at the end. Thank you very much and hope to see you next Monday again. Thank you. Bye.